So we have Andy from King's. He's going to tell us about CFTs.
Thank you, Julius. All right, good morning, everyone, and thanks for coming to the lectures. So we'll be talking about conformal field theories and conformal bootstrap, which is a method to use to analyze conformal field theories. I have decided to be rather explicit in many things. I'm not going to sort of assume too much around this subject, which may be good for some, but boring for others. So the pace might be slow for some people here. I know some people in the audience, and they probably know everything that I will talk about anyway, but then this is really not for them. It's for people that may not be working in this area. And I want to make things sort of explicit because, I've been in many lectures myself, and many times I found myself lost. And when I found myself lost, it's like, sometimes you watch a movie and they like abduct someone, put them in a van, put a hood over their head, right? And then they take them somewhere and they have no idea how they got there. I don't want it to be like this, What's that?
I hope your lectures weren't like that.
Yeah, I hope it's not going to be. Well, some of mine were as a student, but so I don't want to repeat that. Everything I will say, I could say in 1 hour, but the motivation is to have as much interaction as possible and make things as explicit as possible. And you are PhD students now, so almost adults, and you will have the responsibility now to check everything that you hear. And that's not something you learn typically because you read from textbooks and you think that everything they're saying is correct in your previous education. You listen to professors who are supposed to be correct. But as you grow up, you find out that people are not always correct, no matter what their titles might be or their names might be. So, as the old Russian proverb says, you have to trust but verify, okay? And of course, it's not a good policy ever to trust anyone. So if you can verify something yourself, you should go ahead and do it. Now, having said that, of course, I will ask you to trust me at certain points because we cannot possibly just prove everything from first principles. But that's, an invitation for you guys to go back and check and ask questions and, sort of enhance your understanding along with mine, perhaps. If you find something interesting, please share it with me as well. Okay? So, don't just sit there, ask questions, and be engaged. These are recorded, I suppose, unfortunately. So, we'll have to, be civil, but, ask questions. And if I don't know the answers, I will say I just don't know, and I'll check on it and, come back with you next week, or send me an email or anything, like that. I assume you can all find my email. You are, after all, PhD students, and so I will not write it down. And we'll start with some motivation for the study of conformal field theories. And the motivation, at least a very important one, from a historical perspective, is the motivation around phase transitions. Now, when you take matter, you encounter matter in different states depending on the conditions it's found in. Okay, of course, you can change those states by applying, say, heat, or by squeezing something, or doing various things to matter. It changes its state. Oh, I see some other late adults. Anyway,
Wait, you started without being introduced?
I was introduced by Julius, so you can thank him later. So, take a seat, please.
Thank you.
If you missed the introduction, well, you can see it in the video. So, perhaps the most, famous example of this is when you take a liquid, you apply heat, and you turn it into a gas. Okay, this is the first order phase transition because inside this liquid, what happens when you start applying heat is you create little bubbles of gas, right? And those little bubbles sort of expand, and then they get released as water vapor in the atmosphere. And you all know the phase diagram of liquids that we write down. Pressure and temperature is here. There's something like this, where this is the triple point of water, where all three phases coexist. For temperatures and pressures in this range, it's a solid. For temperatures and pressures in this range, it's a gas. And here, in between, it's a liquid. And when you do this, in your kitchen, you're somewhere here, and you are changing the phase of water from liquid to gas. Of course, if you let it cool down, steam will go back. But one key element, and this transition from liquid to gas involves something called the latent heat, right? Even if you bring liquid to 100 degrees, it won't just evaporate. You need to keep adding heat for it to evaporate, because you need to have the change happen to the new phase. But there is a point up here where this line terminates. It no longer goes on, and this is what we call a critical point. This line over here, the separation between solid and liquid phases, always, keeps going on forever, but this line terminates. And up here, there are no longer two phases of water. There is no liquid or gas. It's just one thing, the supercritical phase of water, which you cannot call a liquid or a gas. Okay? The two phases lose their individuality at that point, which is the critical point of water, and there is no, and this transition point over here defines for you a critical temperature and a critical pressure, which is unique for every particular liquid. For water, phase diagram for many liquids will look similar, but this point over here that will exist for thousands of liquids will be at different values for the critical temperature and pressure. So this is what we call a critical point, and we will see that at the critical point, various quantities behave in a certain specified way. In particular, the heat capacity takes this form to a number we usually call alpha in the books, and this alpha, for the case of all these liquids, not just water, but all these liquids that share this kind of phase diagram, takes the same value, 0.11008, and it's believed to be an irrational number, which is a fundamental physical constant, sort of how, other things are fundamental physical constants. And in fact, not just, even pi is a constant, that you could compare this with. It's not like a coupling constant, that takes some value. It is like a number that is independent of everything and only depends on this particular phase transition that is encountered not only in water, but in literally thousands of liquids. So it's a universal number, and it's called a critical exponent. Okay? So this is the behavior of the heat capacity, and there is something that this behavior is something that is found in experiments in, as I said, literally thousands of liquids, but it's also found in completely different types of systems. And there is a whole other class of systems constructed to model ferromagnetism, for example, in which you find exactly the same behavior. And this is what I want to talk about next, unless there are any questions about this. Okay, so this other system that you find this same numbers popping up is called the Ising model. And so here in the Ising model, you can formulate it in these space-time dimensions, and space-time here is kind of meaningless. We're working in a sort of Euclidean context, okay? So there isn't any signs in the metric that could distinguish for you time. So, but it's d dimensions. And we have n sites on some lattice. Let's choose the lattice to be a cubic lattice for simplicity, or hypercubic if you are in higher dimensions. In 3 dimensions, it would be just cubic. And on each of these lattice sites, so there is a variable we call spin, but it has nothing to do with quantum mechanics. It's not, something you apply commutation relations to or anything like that. It's just something that takes 2 values. And it can be for every site labeled by the index I, it could be +1 or -1. Okay? And it has a Hamiltonian, an energy function, which is given by, if you add an external magnetic field, there will be an interaction of all the spins. It will try to align all the spins in the same direction to minimize the energy because of the minus sign, right? In a particular direction, and then there is a nearest neighbor interaction psi Sj, and here this notation means that it's the interaction are nearest neighbor. In other words, it doesn't extend infinitely far away into the lattice, and this J, if it's positive, then because of this minus sign, the spins will want to be in the same direction of nearest neighbors. If it's negative, they want to be anti-aligned, right, to minimize the energy. And therefore, the 2 values give rise to a phenomena of magnetism called ferromagnetism or anti-ferromagnetism. And here there is no real difference for what I'm going to say, but keep in mind the ferromagnetic case where the spins all try to align in the same direction, okay? Now here you see that when the spins all try to align in the same direction, they have 2 choices. They can either align up or down, and these are equivalent configurations of those spins. And so you see the emergence in this model specifically of a Z2 symmetry that relates the 2 configurations, the all up or all down spin configurations. What you also see, okay, I'll continue while they do that. What you also see, well, what I didn't tell you that I want to understand this model. I wrote the Hamiltonian down at 0 temperature, but I want to understand the model at non-zero temperature, okay? And when I go to non-zero temperature, what you know from statistical physics is that it's not the energy I want to minimize anymore, but something called the free energy, right? Which is the energy minus the temperature times the entropy. And it's much easier to minimize the free energy by raising the entropy, right, than by minimizing the energy. And therefore, you see that there is this magnetic field and this J coupling that want to align spins in a certain way, but then the temperature effects want to anti-align them, want to mix them up, because that's what gives the most entropy. So there is this tension between these parameters in the Hamiltonian at 0 temperature and the fact that we introduce temperature. And this is what's going to give us, very interesting physics that we will discuss now. Maybe I should get out of the way until... Okay, now that we're set up, we can continue. So where was I? Yeah, I was saying that in the case where we introduce non-zero temperature, it is easier to minimize the free energy by increasing the entropy as opposed to decreasing the energy. And this is the reason why temperature wants to mix things up, while these other parameters, B and J, want to align things, okay? And this tension is what will give rise to interesting behavior. And the quantity that we will deal with to analyze this interesting behavior, well, is the average magnetization, M, which you take 1 over n times the, here it's supposed to be the sum over I of the spins. And you can relate this to the partition function, which I will write down in a little bit. Where beta is 1 over the temperature, and the partition function is the sum over spin configurations of e to the minus beta h. So every given spin configuration will have some h, some energy, and I'm going to be summing over all the different spin configurations.
Is the partial derivative with respect to b?
Sorry, and beta here, but yes, b here. Yep, thank you. So this is the average magnetization that we will be using to analyze the physics of this system at non-zero temperature. And of course, what you would like to do, if you were, very good and infinitely powerful, is just compute this z, and then just take all the derivatives you want and compute whatever quantity you want. But beyond very specific examples, for example, in this case, away from, if you are in d equals 2, you can do this, and this has a well-known solution. However, if you are in higher dimensions, say d equal 3, starting with the interesting case of d equal 3, where this is not a solved problem, and where you find that exponent alpha that I wrote down there, you cannot just compute this, okay? And so you have to find a way to deal with it differently. And the way with which you deal with this object differently.
Sorry, can I ask
yes.
Why is it that you can't compute it? And what's making it difficult?
So if you don't make any assumptions, so here's the Hamiltonian. You have two quantities, two couplings, and you have the sum over the spins. If you are in 3 dimensions, if you are in 2 dimensions rather, computing this sum, specifically finding the distinct, the field configurations that lead to the same energy, their multiplicities and all that stuff, and the distinct ones, and performing the sums is possible. Not easy, but possible. If you are in 3 dimensions, because you are in more dimensions, there are now
spatial dimensions?
Yes. Yeah, just like in this room, say you had a lattice of points in this room. Yes. If you are now in 3 dimensions, this becomes a much harder problem, okay? The nearest neighbor interactions now extend in 3D. It's not just a 2D problem on the plane anymore. And this results in very hard problems in enumerating the spin configurations that lead to the same energy. And even if you did that in summing up this infinite, it's not, but it's almost infinite. It's, for all practical purposes, infinite. So infinite sum of. That is not to say that it's not possible. I mean, nobody has proven that it's not possible, but nobody has succeeded in doing it.
But in principle, if you had a powerful enough computer, you could just.
In principle, it's a finite problem. In principle, one could solve it, but there is no known evaluation of this partition function as a function of those quantities B, J, and the temperature T that reproduces all the features of the Ising model, for example, this phase transition and so on, in 3D. In 2D, there is. Okay, any other questions? But again, this is not impossible. It's just nobody has succeeded, so feel free to try. Nobody has proven that it isn't possible either. So, okay. So what are we going to do now? Since we cannot evaluate, or we don't know how to evaluate this infinite sum exactly as a function of the parameters, we are going to discuss an effective description. So in an effective description, what we are saying is that we have the Hamiltonian. It's a very microscopic thing because it involves sum over the spins. And now we have also the partition function, which has done all these sums and just gives you a function of, the temperature and also the parameters of the model. We have to find something in between that we are able to sort of apply some tricks to. And that something arises when we think of this partition function not as a sum over the spins, but perhaps as a sum over this magnetization. Different spin configurations will have different magnetizations. So I may say, well, let me forget about the fact that the individual degrees of freedom are these spins. So maybe it's okay to deal with this object here. This object is sort of more coarse-grained because there are many spin configurations that give rise to the same magnetization, right? But of course, there are spin configurations that give rise to different magnetizations. So instead of dealing with these spins, maybe I'll deal with the magnetization. Maybe that will be easier. So let me try and see how far one can get. So instead of having a sum over the spins, over the spin configurations, maybe I'll substitute this with a sum over some function of m, this quantity m, this magnetization. And maybe I will even, if I'm really desperate, make this sum into an integral. Because the problem is very big, there should be a good approximation to the sum by an integral. The magnetization, since the spins can only be up or down, will be something between, by definition, something between 0 and 1. Minus 1 and 1. Okay? So this is the first approximation that we make to try to deal with this.
Is this in a limit where the number of spins is large?
I did not say that, and that's a very good point to stress, that here, for this to work, we have to assume that the number of sites is very large. Okay? Very good. This object over here is what we call, you might call the effective free energy, okay? And maybe you can also define a little f, which is the effective free energy per unit site. So I will talk about either the little f or the big F in the remainder. Okay, so now the question has been reformulated. Instead of trying to compute this over here, we traded it for some other sum, finite sum, but then we said, well, we'll make that into an integral and try to talk about everything in terms of that function f. If I manage to determine that f, I can treat the result of that integral as z and start taking derivatives and compute whatever I want. So that's the logic. How well this works, of course, remains to be seen, okay? Okay. So, how does one typically compute this? Well, there are various ways to compute this. One is mean field theory. You may have heard of mean field theory. The mean field approximation, rather. The mean field approximation tells you that forget about the spins altogether, go to that Hamiltonian we had that involved spins and just write it down exactly in the same way, but instead of using spins, use this M, this magnetization. So here I'm still summing over the spins in the underlying, in the back of my mind. You see no index I here, but this sums over the inequivalent spin configurations that lead to different M's, okay? And then I have some other term here, and then I'm just going to write M squared. Okay? So now I can do these sums because it's the same m. I will assume the same m for everything. Mean field means every configuration gets the same magnetization. So it's another drastic approximation. And then you will say this sums, this becomes just m times n. So this will stay, and I forgot my b here. And then this you write down like this, where this q is the number of nearest neighbors for any site, and that q will depend on the space-time dimension you're in. Okay? Yes? Okay, thank you. So now I can use this result over here to compute that little f over there.
So Q is what I missed?
Q, yes, Q is the number of nearest neighbors to any given site. Okay? Which will change depending on how many dimensions you're in. Okay, so now using this over here, I can estimate this f of m. I can compute actually this f of m. And I find it to be something like minus bm. So this is just now.
So the mean field approximation is the second line here.
Already here I have, so for every spin configuration that I have, and I assume that there are infinite n basically here. So for every spin configuration that I have, I divide the energy by n because I assume that basically there are n spin configurations with the same m. Right? So this second line here is basically doing these sums, pretending that there are so many spin configurations, n, that have the same m, and I compute this. Substituting the spin for m itself is already something very drastic.
Right.
So this taken together is the mean field approximation. And
The value sum is over the I side.
so here, remember, when I wrote down the Hamiltonian, I had a sum over the spins, right? A sum over the spins. And then when you write the partition function, you have the sum over the independent configurations of spins, right? That lead to the same Hamiltonian. So this is similar here.
The value of Q depends on what lattice structure you're choosing, right?
The lattice structure and the dimension of space you're in. Yeah. There is some expression, I mean, I don't have it. One could write it down. Anyway, so now, yes, so now we can go and compute this quantity over here, and you will find that it has this value over here from the contribution of the energy, this little f, and then there are some extra terms here that I'm not going to write them all down, but for example, from specifically evaluating this quantity at non-zero temperature, you get some temperature-dependent terms. Well, the calculation is something like, maybe I'll write them down here. Gives you something like this as approximation. And now what you want to do is you want to find the equilibrium configuration, and for the equilibrium configuration, this f of m, you take the derivative with respect to m, you set it to 0, and you find this solution. So at equilibrium, df dm is 0, and then you find this equation you probably have seen for the magnetization in the mean field limit, that you have the hyperbolic tangent here of beta b. So you have this equation for the equilibrium magnetization in the Ising model.
Not right, so low.
So low? Oh yeah. Yeah, okay. So this is the mean field approximation. Of course, the name approximation is not a very good name. because it's not something you can improve on. We just made some very drastic sort of simplifications of the problem. But it predicts a certain quantity f, then it predicts also, using this quantity, some critical exponents based on the behavior of the various functions that we described. Of course, it gets all of them wrong, but not so wrong. So perhaps it's a good starting point. So how does it predict these critical exponents? The way it predicts these critical exponents is by the so-called Landau theory. So in Landau theory, we use this logic and we say, well, we have some f of m, and here in this case, I'm not going to write the constant term. I will use still mean field theory, and I will expand this over here. So this f of m will have this minus bm term, and then it will have some quadratic term, m squared, and then it will have a quartic term, and so on, just from the expansion around m equals 0 of these various things.
Sorry, is this 1 over 2 or 1 over zeta?
Sorry?
So log zeta minus 1 over 2 or 1 over zeta?
Log 2. It's just log 2.
Okay.
Yeah. Well, that didn't fix it, but yeah, it's not the same as 2. Okay. Okay.
Why not?
It could be, I guess, in some cases. Not identically equal. Okay. So instead of, writing this and performing the calculation, in this case, you can do it, but, you might as well expand it and look at the various terms. And now what you realize is that there is different behavior in this expansion of this effective free energy. And the different behavior comes because the sign of this term over here will determine what the free energy will look as a function of m if I plotted it, right? In particular, if I plot this as a function of m, f as a function of m, there is, I forget about this, set this to 0. So now I have something to plot that's, has a quadratic term and a quartic term. And if this t minus jq is positive, I'm going to have a situation like this. But if t minus jq is negative, the plot will look like this. So here are now two minima. The minimum that you had when t was larger than jq became a local maximum, and two new minima appeared, which are degenerate in energy, where by energy I mean this f, okay, this effective free energy. This is a sign of a phase transition, where our potential, our effective potential, looks like one without, what you would call spontaneous symmetry breaking, when the temperature is below a certain limit, J times Q in this case, while in the other case, when we pass this J times Q, it develops two equivalent in energy minima that are, however, distinct, right? And we have this spontaneous symmetry breaking situation where now our system will have to choose to sit in this state or in this state. Whichever state it chooses has the same energy, so it doesn't matter. But these are inequivalent configurations of our system. And so this mean field example is used typically because it captures this behavior. Of course, it's an approximation that is not something you can expect to compute things with and have good agreement with experiment, but it captures this qualitative feature of the phase transition. Okay, any questions?
Does this expansion, so you need t to be large to have m closer to?
Yeah, I assume that m is something I can expand around 0, basically.
But if t is small.
And jq is what sets the scale for what t large. T is a dimensionful quantity, and It doesn't really make sense to call it big or large or small, but you can divide it by JQ, and now you can call this, you know.
But if T is small relative to JQ, wouldn't M be closer to 1 or minus 1? Because the spins would line.
If the temperature is large, you are in this situation where the spins are, random. They don't want to be aligned. Temperature effects, temperature fluctuations are large and cause them to be in this high entropy state.
Yeah.
But as the temperature comes down and crosses that value,
I see.
then this quantity J wins in this game, right? And now it gets to align the spins in one or the other direction.
But when you made this approximation, you were saying M was close to 0, and now you're saying M is
minus 1 or 1,
yeah.
basically, in the minimum, yeah.
So is the approximation valid? But do you need M to be close to 0 to make the approximation?
Yeah, this approximation over here is showing you the qualitatively that something happens at some critical value of the temperature. This is the reason why it's used. It shows you that in the free energy, when you expand it like this, you get this type of different behaviors. Now, the approximation, if you're asking if this, we don't have a good understanding of what this series looks like asymptotically, and if you can resum it and do things like that. Of course, in this case, we know the answer, but the logic will stay the same for other cases. And the approximation that we made here, there was no approximation that M has to be, it has to be between minus 1 and 1. Of course, you have some logs here, so you have to be not hit those numbers. But the expansion is showing that even at the leading M squared and M to the 4th order, the qualitative behavior of the potential shows this difference that the phase transition, that you get from the phase transition at this critical temperature. Of course, this is not the full picture. You would have to go and plot this thing instead. But I'm just saying that in this approximation, you can already see that something is happening due to the tension on the M squared, the term that you have here, and the M squared term that's hiding in here.
I guess what's confusing me is it seems like you're assuming M is small and then concluding that M is not small. You're assuming M is close to normal to start with, and then you're concluding
Yeah, I mean,
that M is close to 1.
I basically expanded this,
Yeah.
basically just a Taylor expansion of this.
Wouldn't you need
Which-
more terms to really...
If this, you're right that if you go farther out that this is not reliable and starts to become unreliable here, but what you do see is that at M equals 0, very close to M equals 0, you will see that the potential here it curves up, while here this former local minimum is now a local maximum. So some other behavior will have to occur, and you can analyze the potential at high M and see that it does something like this. So in order for it to match, it's got to do something like this. So this is sort of the picture. Very good.
We are assuming J positive here, or not?
Yeah, this is the ferromagnetic case in which J is positive, yes. Okay. So this is the idea around mean field theory, but now Landau and took this idea and ran with it and said, even if I don't have mean field theory, no explicit expression for this f of m, I will assume that there is such an f of m for any system I write down, and that it has an expansion in terms of this quantity m, which you might call the order parameter. You might have heard, referred to it as an order parameter, and that will have an expansion of this type. And I will be able to predict critical behavior in systems by analyzing the potential in this sort of similar way and seeing if I have this change in the way the potential behaves. So this is the Landau theory of phase transitions. This is the basis of the Landau theory of phase transitions. And what people refer to as the Landau-Ginsburg theory of phase transitions sometimes is something a little different, where instead of taking this m to be the same for the whole lattice, then you say, I will also promote this m to a function of x. So now m is not just some global quantity, but it's a local quantity. It depends on where I am on the lattice, where x is the point in space that you are as you travel around the lattice, M will be different. So the idea of this Landau-Ginsburg theory is to take this M and make it into a field, right? And so this gives rise to this whole basically subject of statistical field theory that is applying Landau-Ginsburg theory and other methods to analyze critical behavior. And there are various assumptions that we typically make about what that M of X, so let me write something, what that M of X
would the functional form of M of X be related to the spin configurations with that M itself?
Well, at this point, everything has become sort of abstract. The origin of M is, spin configurations and their magnetization. So here you may try to understand M of X in a similar way, where you say, I have some lattice, something like this, and I'll make boxes of things. But the boxes are not just going to be small boxes. I have infinite lattice sites, essentially, very large number. And these boxes also contain a very large number themselves. So basically, this will give you some position where you are. And then within the box, you sort of operate in the same way. Right. And in that sort of sense, you substitute M by a function of M of X. Okay, so it's sort of a similar, it's sort of this logic where since you have this very large N, you can make a very large number of boxes, each one of which has a very large number of sites in it, and you sort of apply the same logic as before. So this is Landau-Ginsburg. Okay, now what is this F gonna look like? There are various assumptions on what this F might look like. One assumption is locality. It's a local function of this M of X. So let me make some.
This leads to the critical exponent that we found that you mentioned before. The same value.
Not yet, but yeah, we'll see how. We'll see in a little bit. So this F so it has various properties. It is a local function. We will assume translation and rotation invariance for this quantity. So now we don't have any computation of this F. It's some general system that we're trying to write an F for. And the assumptions we make is that it is local. There is translation and rotation invariance. In this case, we have this Z2 symmetry.
What does locality mean in this context?
Sorry?
What does locality mean?
That it's the ddx integral of that you can write it as an integral over the whole space of some other function. And analyticity, it's a very important one. So it's analytic, meaning that you have this M, but you don't have things like the square root of M. You don't have strange things like that, or 1 over M. You don't have behaviors like that. There's no proof of any of this, but these are sort of the rules of the game. Okay, and these are assumptions. And also, what else do I have here? That that sort of you can have derivatives of this M, since now it's a function of X, but M is supposed to be sort of a slowly varying function of M, and so you can rank the importance of derivatives by how many there are. The first derivative will be more important than the second derivative, and so on. Okay, so there is some sort of derivative expansion that you can make. Okay, so these are the ingredients of Landau-Ginsburg theory, and now you can write down various systems, try to understand various systems, look at the free energies, apply these sort of I don't know, assumptions, and try to see if they have critical behavior and compare with experiment.
I have a quick question.
Yeah.
When you say generalization and rotation, sorry, you're taking x to be a continuous variable, not on a
Yes. It emerges sort of in the continuum limit, if you want, yeah. Okay, so maybe this is a good point to take a break. Are we supposed to take a break? No. I could keep going. Okay, let's take a break for 10 minutes, right? And return basically at the top at 11:30. We finished by talking about how we promote this magnetization to a local quantity of where we are on the lattice. So basically, so now, you know, instead of m of x, I'll just call it phi of x, because that's what we usually do. Oh, and by the way, I should say that, you know, I omitted a lot of the details here about, say, the calculation of that free energy in mean field, which you know, amounts to computing some sort of entropy for these different configurations and so on. But a lot of all of these details and all of this material can be explained, you know, in very good. Is explained in very good detail in some lectures by lecture notes by David Tong, and you can find those online, called Statistical Field Theory. Okay. Okay. So. Very good. So this z, the partition function that we had before, remember, was an integral of this little m, which was independent of x. Now it's going to be an integral over this function of x, so it's going to be a path integral. And this is where you get sort of a path integral description of this statistical physics models, where instead of h bar you have this beta, but there is a difference in that in the statistical physics models this f also has beta in it, while the Lagrangian, say, of any field theory does not have h bar in it. Okay, so it's a little different, but the logic is rather the same. Okay, so so already from the so suppose you took this function of f over here, and you did this expansion that you know, in Landau-Ginsburg theory we're supposed to do. We're going to write this now as some integral because we want it to be a local quantity. We will write it as an integral, and we will only keep the quadratic terms, like this, okay? And in this effective free energy, we can ask what is the correlation function of phi, for example. You can compute things like the 2-point function of phi between 2 points x and y. This will give you a sense of the correlation of spins, if you want, in or magnetizations in these different boxes that I was drawing here. Okay. And to do this, you know, you may introduce a source for this over here. Maybe let me write down the source. Then I will take two functional, so now I take this, I put it up here, right? And I will compute the 2-point function using the standard sort of path integral description of how you do this. Is you take functional derivatives with respect to the source of this, you bring down 2 powers of phi at these two different points, and then you set the source to 0, and you have your correlation function. So this I will call g of x minus y, and since we assumed this translation invariance, it will only depend on x minus y, and in fact it will only depend on the norm of that vector, since we also have assumed this rotational invariance. Okay, so what is this? How do we compute this? Now let's go to the set y is 0. I can always use translational invariance to go to the point y equal to 0. And let's define a quantity xi, which we call root gamma over mu, where gamma is this quantity over here in front of the kinetic term. Okay, then this g of x, as I said already, it's going to be just a function of r, which is the norm of x. And I can compute it in the standard way. It's going to be some integral like this. Okay, so this is the 2-point function. All I have to do is compute this Fourier space, this momentum space integral. And the way one does this is by using a trick, which if you have not seen, maybe it's good to see. So the trick is to do the following. You say that 1 over k squared plus 1 over xi squared is equal, has a particular integral representation okay, this is just an identity, and now I can use that to substitute that denominator in. Then I'm going to change the order of the integrals. Okay, then I'm going to complete some squares. It's a good exercise to do yourselves. And after you complete the squares, you can do Gaussian integrals at that point. You can perform them explicitly. You're going to be left with a t integral, which takes this form. So let me write down the final answer, and you can check it. Maybe I'll write g of r is equal to 1 over gamma 4 pi to the d over 2 integral from 0 to infinity dt So this is the answer you get after you do all these manipulations. And this has a name. You can write it as, so that thing over there is equal to oops. Times k of 1/2 d minus 2 of r over xi, where k is an elementary function, the modified Bessel function of the second kind. Okay, so that's the answer. Now you have computed it, and it's given as a function of r over xi, a dimensionless quantity, r over xi. And now what you can do is you can look at different limits of this. And it turns out that if r is much smaller than xi, this has this particular form.
The coefficient is an r or a gamma?
This one is r. Yeah, gamma went in here in this xi. Yeah. While if in the other limit, where r is much, much larger than xi, you have a very different behavior for the two-point function. Like this. Okay? And we see, very different qualitative behavior in the correlation function depending on this quantity xi, which is still there, is defined by as root gamma over mu. You see again the coefficient of the kinetic term and the coefficient of the quadratic term. This is a quadratic free energy, so we can perform all these calculations exactly, basically, and we find that the correlation function has this very different behavior depending on if we're looking at length scales r that separate these blocks of spins, what I was drawing before. If those scales of separation are much smaller than some characteristic length scale xi given by that combination, then we see a power law behavior in the two-point function, while if it's much larger than that xi, we see an exponential suppression of the correlations. Okay? And
So what was the definition of gamma again?
it was in the coefficient of the kinetic term. It was gamma del phi squared.
And how is that determined? Is that
In the free energy expansion, right?
yeah?
It will have some coefficient, and it's that coefficient.
Okay.
If you can rescale the fields, but then it will appear in the other. You can rescale the fields if you want to eliminate it, but then it will appear in other parts of the effective action. Right? Okay, so why did I do this? Because it turns out that whenever we reach a critical point, the correlation, there is a characteristic length, the correlation length, typically called the correlation length, in which the interactions, which goes to infinity, which means that the interactions become scale invariant. So you reach your critical point, the interactions become scale invariant, meaning that there is a correlation length xi that diverges. And since that correlation, and this correlation length is exactly the same, it diverges, and therefore all the distances are smaller, much smaller than this thing that diverged, and therefore in a conformal, at a critical point, the behavior of the two-point function is of this type. There is a power law behavior that you encounter, and this is again here a hallmark of critical phenomena associated with the scale invariance that emerges at the fixed point. Okay, and here we see a specific power, d minus 2 for the exponent. However, this is not a power that remains so when we consider theories that have interactions. So to write down that effective action I erased, I stopped at the quadratic term, so I did not allow any interactions. However, when you add interactions, this power over here will be modified. It will pick up an extra contribution related to the anomalous dimension of the field and so on. And perhaps the easiest way to sort of discuss this is to now switch to a description that is a field theory description. And this is sort of like, a logical jump. We went through quite a few logical jumps, from spins to magnetizations to local quantities to thermal like path integrals and so on. And we saw that in different regimes there are behaviors that are qualitatively very different. We saw, for example, how there is a critical temperature in which there is a change in the form of the potential. Here now we see that the correlation function will behave very differently depending on what length scales we look at. And the types of systems where this happens are very common, and we find through experiments that a lot of them share the same behavior. So modifications to this power that arise from interactions are the same if you consider that water system that I told you about in the beginning, or the Ising model that we also discussed. And this gives rise to this idea of universality, where in these types of systems, the behavior that emerges does not depend on sort of the underlying degrees of freedom. If you have water molecules or if you have spins on a lattice, it doesn't depend on any of that. The interactions are so special in some sense that they take a universal form, and this universal form this is described by a set of numbers which are unique to that universality class that we now want to compute among different quantities. And the essential features that dictate the universality class you're in are basically the type of order parameter that you have. In the case of water, the order parameter is just the density. Here we had this magnetization, that's the order parameter, and symmetries that order parameter has to obey. For example, in the Ising case, we had the symmetry that was the Z2, the Z2 symmetry. And to see corrections to this, you have to consider the so-called denormalization group, which I don't have time to go through. There's again a good discussion of this in David Tong's lectures. But here I just want to claim that there is another theory in this universality class, and this other theory is obtained in a rather fancy way, where you write a Lagrangian down of a scalar field phi, and we're Euclidean, so I'm going to write it like this, plus some interaction, and well, maybe there is also a term like this. So what I'm going to do is start with the free theory and try to perturb it by this operator over here. Now the dimension of a field phi is d minus 2 over 2, determined by wanting this term over here to have dimension 4, so that I can stick it into an action, right, which I can stick into a path integral. So if I were to do this in 3 dimensions, as we have been doing so far, this would be a dimension 1/2 field, and therefore the dimension of phi to the 4th is 2 times d minus 2, it's 4 times this, right? And in d equal 3, this would be 2, which would be a very strongly relevant operator, meaning that if I added it to the Lagrangian, it starts a flow, an RG normalization group flow, which is a very strong flow, and there is no perturbative way to analyze that flow. So what to do? There was a rather, crazy idea by Wilson and Fisher more than 50 years ago now, to try to understand this not in d equal 3, but in d equals 4 minus epsilon. So you go to d equal 4 minus epsilon, and now this over here becomes 1 minus epsilon over 2, and this over here becomes 4 minus 2 epsilon. And 4 minus 2 epsilon is smaller than 4 minus epsilon, but only slightly so if I assume that this epsilon is small. Okay? And now I can use perturbation theory to analyze the flow generated around the free theory when I perturb by this operator. To avoid having to deal with phi squared, which is a strongly relevant operator, I will set its mass to 0, okay? And I will be analyzing the flow in the space of this coupling lambda. Now, the flow is captured by something called the beta function, which turns out to be minus epsilon lambda plus, at one loop, there are corrections to higher order here. Okay, so what we observe is that this beta function has 2 zeros, one when lambda is 0 and one at the non-trivial value of the coupling lambda. And those non-trivial zeros correspond to solutions that have emergent scale invariance. Now, I haven't proven any of this to you. We don't have the time, but this is sort of the story, and you are invited, of course, to look into the details in the various books. And so here for beta equals 0, lambda star is 0, or lambda star So we found signs of a non-trivial fixed point, and the claim now is that universality is such that this fixed point in the limit epsilon to 1, which doesn't make sense, is in the same universality class as the fixed point of water that we discussed and the fixed point of the Ising model that we discussed. That's the claim. There's no proof of this claim. Okay. Nevertheless, if I now start to compute those critical exponents like that alpha there that we had before, I can do it within this context. And what I will be getting are solutions that are series in epsilon, in this epsilon. And then what I will do is I will say, well, maybe compute a couple of orders here, right? And then I might just, send epsilon to 1 and see what happens.
How are we justified in doing that?
We're not, but we're going to do it anyway. And when you do it, in fact, it works very well. So that number that I wrote in the beginning, that 0.11008, that critical exponent alpha, is reproduced very well by this type of construction when you send epsilon to 1. And maybe, you perform a certain resummation before you do it. Maybe you pretend you know what you're doing, but you don't really. But anyway, this is not. There is no proof that this is even in the same universality class. But it has the Z2 symmetry that we argued in the beginning. It has a scalar order parameter. So there are reasons to believe that, since this conformal behavior is emergent and sort of universal, that this lies in the same universality class because we have a sort of similar starting point that physically maps to the physical systems that we were discussing before. There's no strict proof that the epsilon to 1 limit makes sense. However, you can prove some resummability criteria for this. The series that arise are Borel resummable, and maybe you can make sense of the resummation in the limit epsilon to 1. But what shows that this is a good thing to do is basically that it works very well.
When you say that it works very well, it reproduces something.
It reproduces, well, yes, a few digits of the critical exponents, like this alpha. Of course, these days, we're going to get to it. There are better methods to do it, the conformal bootstrap, which we'll get to by the end of the lectures. But,
methods to do what?
Sorry?
To obtain that number.
To obtain that number, yes.
Right.
That alpha. There are much better ways to do it. But the fact that this even gives you this fixed point over here, that tells you that there is something non-trivial happening in this Z2 invariant theory is already rather suggestive and rather surprising. And it turns out to work very well in many other examples. The point is not to consider the epsilon expansion, but I just wanted to show it as a way to determine this alpha exponent that we had there before by assuming all these universality ideas and so on. Okay?
Why it works remotely well.
But
Is it understood why it remotely works well at all? Like, mathematicians actually sat and thought about it properly.
there have been, various studies, for example, to prove that the series are resummable in some sense and so on. But why it works, I don't think there is a mathematical there isn't a theorem like that. It's sort of like symmetries match, special conformal symmetry is special, and many systems belong to the same universality class, and these systems happen to as well. But this epsilon expansion goes well beyond this particular example. There are many other theories that that one could describe with the epsilon expansion. In experiments, there are cases where the experimentalists see no phase transition, for example, and you can apply this epsilon expansion and find that there are actually no such solutions. So it works very well. Nobody knows why in a strict sense, but from physical intuition, it relies on these ideas, right? We have some free energy there that we expand. We do all these Landau tricks. Well, here we have something similar, right? And there is sort of a mapping of the statistical field theory language to this, normalization group-like language. But beyond that, I don't have anything more. Yeah.
I'm wondering why this D is said to be 4 minus epsilon rather than 3 minus epsilon.
Yeah, because I want to make this operator only slightly relevant, meaning I want its dimension to be perturbatively away from the free theory dimension, right? So you see here, this phi to the fourth operator, if it was a marginal operator in 4 minus epsilon dimensions, it would have to have dimension 4 minus epsilon. Here it doesn't have dimension 4 minus epsilon, it has dimension 4 minus 2 epsilon, which is smaller than 4 minus epsilon, but only by epsilon, right? And this fact, that the distance of this operator from the marginal operator is only epsilon, allows me to set up a perturbation theory that I can work out in terms of Feynman diagrams. So the only reason is because that's the way I know how to do anything. And then I do it, and then, you know, I go and forget that I did that, and then send epsilon to 1 in the end. And this works surprisingly well. But the original reason why I wanted to go below 4 minus epsilon is because the dimension of this operator is then close to marginal. Yeah, it's a technical sort of requirement for these calculations to be able to go through.
So if I want to deal with other examples or other theories, then I need to adjust this 4 to other numbers.
So, for example, if you had a phi to the 6th term, suppose there was no phi to the 4th term, right?
Yeah.
Now, it turns out that you have to consider these models in d equals 3 minus epsilon. Because, you know, if you were to compute if you were in 3 dimensions, right, the dimension of the operator phi would be 1/2.
Yes.
Sorry, it would be 1 minus epsilon over 2, right, in 3 dimensions, in 3 minus epsilon rather. Let me just do it. So if you went to d equals 3 minus epsilon, then delta phi is 1 minus epsilon over 2. So delta phi to the 6 is 6 times this, right? So 3 minus 3 epsilon. And again, now you're 2 epsilon away, but still you can do perturbation theory. Well, if you tried to do 4 minus epsilon here, and you computed this delta phi to the 6 would be much farther. It would be an integer farther, and some epsilon stuff. But we want to be far by just something order epsilon. We don't want to be far from the marginal operator by an integer, because then we cannot do perturbation theory. Okay? And another case is phi cubed, then you would have to be in 6 minus epsilon. And then all other cases have to be in fractional dimensions to work. Yep.
If you take this and then set epsilon to be -1, does it work?
Yeah, you can do that. Yeah, it works. In the sense that there are models that you can define in higher dimensions, say 5 dimensions, where you send epsilon to -1.
They're both complex numbers.
And I haven't seen much of a motivation for considering complex epsilon, but there could be one, I don't know. But in principle, yes, you can go to higher than 4 dimensions using this logic.
Obviously, you have to do some sort of numerical 5D thing, but it would match just as well as when you go back down to 3D.
Yeah, in fact, it's even more than that. Like, you can go to 4 plus epsilon with the motivation of going to 5. And what happens is the fixed point that we were discussing here, the non-trivial one, becomes the operator phi to the 4th becomes a relevant operator at this point. The stability properties sort of change. And instead of flowing from the free theory to that point, then you flow from that point to the free theory. But then you can ask, is there a theory that has this point as an IR point, like this one? And in fact, you can find a theory like that in 6 minus epsilon dimensions. And then you send epsilon to 1 from there, and you find that the same fixed point is obtained as an IR fixed point of that theory, but it's a UV fixed point of this theory. So it provides sort of UV completion of that.
And if you went even further, you went epsilons 2.
Yes, you can epsilon 2, you can do 3, you can do whatever you want now. Works. You have to be careful. Works is a strong word. I mean, it works for some things, it doesn't work for others.
Still looks reasonable.
But there are reasonable things. For example, with the 6 minus epsilon thing that you can start with phi cubed in 6 minus epsilon, you can set epsilon to 3, go to 3 dimensions, and predict things about something called the Yang-Lee edge singularity, which is a non-unitary theory. There are various settings in which this example works, but by no means, does this work no matter what you do.
Yeah, okay.
It isn't something, but there are contexts in which these types of epsilon expansions work But it doesn't necessarily mean that it's going to be the same theory. You may have to be creative in what you try.
Right, I see.
Okay? And since there's no proof of any of this, it relies on the results to show that, you know, what you're doing sort of makes sense.
Right, so matching them.
Yes, yes. Matching the physical behavior and matching, if you can, critical exponents, or giving some qualitative features of them that have to be satisfied to show that this makes sense. Okay, so what this method relies on from this example over here is this idea of the normalization group, where we have some sort of scale, mu, which is an energy scale at which we study a system, and we start from a theory in the ultraviolet here. When we deform that theory, just like we deformed the free theory here by the 5 to the 4th operator, we start a flow described by this beta function, right? So now we have the space of theories parameterized by, you know, where we are along this flow, which then terminates in the infrared to some other conformal field, some other theory with this beta function is 0, which is perhaps non-trivial. And then this defines the IR limit of the flow. And as it turns out in these models, the UV and the IR limits are conformal. So we had the example where that correlation length xi was going to infinity, and we said how that's scale invariant. In fact, the UV and the IR fixed points are not just scale invariant, they are conformal. And we'll see what that means starting now. But what I wanted to say is that all methods in the literature with which you analyze, you know, fixed points, you compute these critical exponents like that alpha, all of these methods rely on this same idea. You have some theory, you deform it, you flow, and you try to find a fixed point that you end up in the IR. Now, this is not the logic used by the bootstrap at all. But all methods before the bootstrap used this logic, and they could be non-perturbative methods as well. For example, Monte Carlo simulations of this type of systems also use this logic, where you start from a known point, you deform, and then you try to tune things so that you end up in a non-trivial you know, interacting. Non-trivial means interacting infrared fixed point. So you can see sort of the problem with this, because if I want to compute an exponent like alpha, I want to compute it here. Why do I have to do all this? In principle, I should be able to compute it just by knowing that there is a theory. Now, this is an assumption. Suppose there is a theory, a conformal field theory. I know from intuition that it comes from some endpoint of some renormalization group flow. But suppose I just assume that there is a conformal field theory. I should be able to compute that alpha within the conformal field theory without computing some beta function and getting to that conformal field theory somehow, right? So this type of method would be using conformal symmetry from the very beginning, right? Because we are at the fixed point, while here, the conformal symmetry that we got is only emergent at those points. So it's clearly of benefit to find such a method. And that method was not only something that people seeked for conformal field theories and critical phenomena, but also in other areas of physics where you think that systems are so constrained that imposing consistency conditions that they have to satisfy might fix at least some of the solutions that are possible, right? The first sort of program that tried to use this was the S-matrix program in the 60s, way before your time and mine. People were trying to use analyticity properties and unitarity properties of the S-matrix, impose those conditions on what the S-matrix might look like, and try to get answers of what possible S-matrices there can be. Okay? And it was a big program, but of course, you know, after the standard, QCD and the standard model and all that, people learned how to do things within quantum field theory as we know it today. It sort of fell out of favor, and there was a proposal by Polyakov that said that something similar like this bootstrap method, something that relates to consistency conditions of the theory itself, might be constraining enough to determine things like critical exponents. So he made that suggestion. He wrote some equations down. The equations, of course, were horrific. So there was no progress dealing with them in an analytic way until much later, a little more than 10 years later, where people realized how to understand these equations and put them on a computer that could then solve them and determine, just using conformal symmetry and these consistency conditions, determine critical exponents like that alpha. So this is what we want to get to by the end of the lecture. This was sort of an introduction about the past. So now I want to start sort of setting up the ingredients that we will need in order to understand, this conformal bootstrap method. Okay, are there any questions about this so far? Yes?
Do RG flows always have well-defined CFTs that you use in IR lengths?
With various assumptions, it is widely believed that it is so. For example, you have to assume unitarity, you have to assume some things, but there is no fully general proof that this is the case either. Except, maybe in some specific settings in 2 dimensions. But beyond that, there is no general proof that the RG flow can only end at a fixed point.
But it can run away.
Well, yeah, there could be the trivial case, of course, where it doesn't end at a fixed point. But there, you could envision other asymptotics like, limit cycles. So you could envision all sorts of other asymptotics. No such examples have been found in, in field theory, and there are no, no proof that it cannot happen either. Okay. So, I hope the logic is clear. We want to deviate away from this example where we find beta functions, we think about RG flows, we do things like that to eventually get to the fixed point. What we want to do is use conformal symmetry. So let me introduce what this conformal symmetry is by talking about conformal transformations of space. Now, conformal transformations are defined So conformal transformations are defined by changes of coordinates. So here we have our coordinates x mu, which go to x prime mu of x, such that the length elements only change by a function of x. I will just denote it as omega x squared, omega of x squared. This is the definition of what we mean by a conformal transformation, and dx squared here is eta mu nu dx nu. Here I can use a Minkowski metric if I want to, which I might take to be -1, depending on how many dimensions you have. It can be of this form, okay? Now you can define this in any dimension you want. You can define transformation of the coordinates such that the lengths only get rescaled in this particular way. And now what you want to do is, of course, you recall from your first classes in special relativity that you know such transformations already, where this omega of x is 1. And we call those Lorentz transformations, okay? So rotations and translations, Poincaré more generally, rotations and translations will have this omega equal to 1. But the question is, are there transformations beyond those with some non-trivial omega? And to solve such problems, what we do is we consider the infinitesimal form. In the infinitesimal form, we take this x prime mu to be x mu plus v mu of x, where now we assume that this is a small vector in some sense. And then we write this omega of x as 1 plus sigma of x. Sigma is a scalar quantity, and we take it to be small. In other words, we will not keep anything that is sigma squared or v squared or any higher powers of these quantities in the expansions. Okay. So what do we do with this? Let's see. So what do you do with this? You take this equation and you write it using this expansion, and what you find is that let's see. You find that on the one side you have this becomes which we don't care about, and then omega x squared is of course just 1 plus 2 sigma of x plus order sigma squared. And now these are the ingredients, you stick them into the equation, and you find that 2 times d mu v nu dx mu dx nu so using these equations, substitute them into that over there, and you find this. And now you want to take away the dx mu and the dx nu, and that will allow you to only determine the symmetric part of this, so that d mu v nu plus d nu v mu is 2 sigma eta mu nu. So the infinitesimal parameters of the transformation v and sigma satisfy that equation. Okay? And from this equation, I can take the trace, if I want to, meaning I can multiply with eta mu nu and contract. And this tells me that the divergence of this d mu v mu is d times sigma. Okay? And now I can use that sigma over there, plug it into here, and get what's called the conformal killing equation. Which says that d mu v nu plus d nu v mu is 2 over d eta mu nu d rho v rho. So this is the conformal killing equation that we want to solve. If I find these v's that satisfy that equation, then I can take the divergences and I can find the sigmas, and I know all the possible transformations that satisfy this equation over here. Okay? Okay, let's do that. This is an equation with, one derivative. So it shouldn't be too hard. Nevertheless, I don't know, you can make an ansatz about what that V might look like and stick it in and try to determine things that way. That's one way to do it. In most treatments, people play, in most books, people play games to solve this equation. And a particularly perverse one is the following. You start by saying, I want to determine this d rho d nu v nu, and I will write it in some weird way where I will take a certain cyclic permutation of indices to relate it to the left-hand side. So I will write it as follows. Let me see. So let me write it. Okay, I can write it like this, and then I can use the equation to show that this is equal to d rho sigma eta mu nu plus d nu sigma eta mu rho minus d rho sigma, d mu sigma, eta nu rho. And now I can act with d mu on this. And you will find, so the d mu on this side will go through this stuff and will give me just d rho d nu on sigma up to some factors. So let me write it like this, d rho d nu sigma. And then on the other side, I'm going to get twice d nu d rho sigma minus eta nu rho d squared sigma. And now I can bring this over to this side and say that d minus 2 d rho d nu sigma is equal to minus eta nu rho del squared sigma. Now I can take the trace of this. Okay, and when I take the trace of this, I will find d minus 2 here times this. Here I'm going to have a factor of d, and this will become twice d minus 2 when I bring it to the other side. So it's going to be d minus 1 del squared sigma is equal to 0. So that's one thing that I find. And then I can use this thing over here again to get the following equation. To get that d minus 1 times d minus 2 d rho d nu sigma is 0. Now this is relatively easy to solve, okay, for that sigma. Of course, if d equals 1 or d equals 2, I cannot then say that d rho d nu sigma is 0. But so for d other than 1 and 2, this implies that d rho d nu sigma is equal to 0. So now this is easy to solve. And once you solve it, you can find the v mu whose divergence gives you this sigma and proceed that way. Obviously, this is a second order equation, so sigma, to solve it, let me write down the parameters. It can be at most linear in x. And typically people write it in this form. It's a scalar, so you have to contract the indices. And using the equations that I have written there, you can find, so there's a few steps here that I will not repeat, but you can find that the v mu of x, the most general solution of it is the following, is a mu, which is just some constant, minus omega mu nu x nu, where this is antisymmetric, plus kappa times x mu, plus b mu x squared minus 2 x mu b nu x nu. And this is the most general v mu of x that solves that equation. And these have names. These are translations. This we know already, and they correspond to omega equal to 1. These are rotations. These are dilatations. And these are called special conformal transformations. Okay? Now, if you are in d dimensions, translations will give you d. You have d direction, so you'll get d. The length of this vector will be d. From rotation, d parameters. From rotations, you get 1/2 d times d minus 1. Since this is an antisymmetric d by d matrix, from here you'll get 1, just this kappa. And from here you'll get another d, right? So when you add all these up, you see that you look at the algebra, which we will look at next time. you have 1/2, what is it? D plus 1 times D plus 2 generators which generate the group SOD, 2, which is the indefinite orthogonal group. Okay, we'll see how that arises from the algebra, but I don't think we're going to have enough time to do it today. But before we finish today, let me take 5 minutes and just describe what these transformations are. Of course, we know what translations and rotations are, and to find what we only wrote down the infinitesimal form, but now we want to understand what the finite form of these transformations are, and to understand the finite form, we have to solve for the so-called integral curves of the transformations, right? This is the standard way you convert from the infinitesimal to the finite form of the transformation. So solve for the integral curves, which means that you have to solve some differential equation. By definition, I will use these dots for the time derivatives. Okay, so we need to solve this differential equation to determine the finite x mu's. And if we were to do it, it's very easy to do for dilatations. Dx mu over dt would then be kappa times x mu. And from this we find the solution that x prime, x mu at time t is e to the kappa t x mu at time 0. And now you might choose t equal 1 to call x prime. Okay, so this becomes x prime mu is e to the kappa x mu. So this is the finite form of the dilatation transformation, whose infinitesimal form is described by that vector kappa times x mu, which tells you that basically what dilatations do is they take a coordinate x mu and homogeneously rescale it by kappa, e to the kappa, rescale it by a positive number. Dilatations do dilatations. So they got their name this way. What's more tricky is to see what special conformal transformations do, okay? And I'm going to finish with this. So special conformal transformations, so these are the dilatations. So these special conformal transformations, I'm going to analyze them here. Now we have a much more complicated differential equation to solve. Let me just write it down. Dx mu dt is going to be given by that vector over there. D2. B, what is it? B mu, I can see it from here. B mu. B dot x. Okay. So this is the vector. We're going to solve this. Now it's not easy to solve, okay? But there is a trick, as always. If you try the change of variables, define y mu to be x mu over x squared, okay? Then it becomes like a translation, okay? Then it becomes dy mu dt is equal to some constant vector b mu. So it's a translation, but not in real space, but in inverse space, okay? As defined by the inversion going from x mu to x mu over x squared. So now you can solve it here and bring it back after you solve it. And what you find is, just let me write it down, that the finite form of the transformation is x mu plus b mu x squared divided by 1 plus 2 x dot b plus b squared x squared. So this is it, okay? So if you wanted to say something about what this does, what would you say? What would you say?
It is an inversion, then a translation, then an inversion.
Yes, so it translates, but in inverse space. So if you were to say that the translations move 0, right? When you translate in real space, you move 0, but you fix infinity. You don't change infinity when you translate in real space. Conformal transformations are weak transformations that move infinity and leave 0 fixed. Okay? So if you want to say something fancy, that's what you say. But The origin of this is, of course, that they can be written as inversions, then translations, and then inversions back. Okay? All right, so these are the transformations, and perhaps I'm out of time, so I shouldn't keep going, but next time we'll start looking at the algebra, how these transformations that we know now we know how they act on space-time. We will learn how they act on fields, and start talking about correlation functions and so on. But that's next Monday. Right? Next Monday, right? Yeah.